It's time to look at the new I/O interface and try the new async await mechanism. This is not going to be a deep dive since this is still in development, but I want to get a taste of what's happening and what we can expect for the next Zig version. Alright. If we look at the documentation, std.io is described as a cross-platform interface that abstracts all I/O operations and concurrency, including the file system, networking, processes, time and sleeping, randomness, async, await, concurrent, cancel, concurrent queues, wait groups and select, mutexes, futexes, events and conditions, and memory map files. So all that in one big vtable. I mean, look at it. It's a big boy. The idea is to gather all long-running tasks or tasks that can block the main thread of execution in this vtable, and then let the implementation decide how to handle these tasks and what to do when they block. But unless you want to implement your own I/O strategy, we can mostly ignore it and focus on how to actually use an existing I/O implementation. You know, I suspect that a lot of things we were doing before is going to pretty much be the same, but will require an I/O parameter. For example, take a look at the file system. Before, or I guess currently, we would use functions and types defined inside std.fs, but now it's almost empty and almost everything was moved to std.io file or std.io dir. And if we look inside, it's pretty similar, but we now have this I/O parameter. The easiest way to get an I/O implementation is to use the juicy main. I made a video about it, but real quick, the main can receive an argument of type std process init, which contains an I/O implementation. By default, it's std.io threaded, a multi-threaded I/O implementation. But if you don't want to use the juicy main, you can initialize it yourself using .init and then call the I/O function. Note that it requires an allocator and you should de-init it too. If you prefer, you can use a single-threaded blocking I/O implementation by using .init_single_threaded, or you can also use the evented implementation based on I/O uring on Linux or Grand Central Dispatch on Mac OS or KQ on other operating systems. And for our test, we can use the testing I/O. So let's try it by printing hello world to the standard output. So let's define our main function with the init parameter of type std process init. Let's copy init.io for convenience. Then we can write to std out by getting its file handle with std.io file.std out, and then calling write streaming all with the I/O implementation and the hello world string. And that's pretty much all you need to do with this new I/O parameter. Not too difficult, right? Okay, I just want to spend a few instants to talk about why I'm using the write streaming all function. I'm sure some of you already know this, but because I didn't talk about it in my video about the new reader and writer interfaces, I want to do it now. If you look at the documentation of std.io file, you will see two types of writing and reading functions: positional and streaming. The difference comes down to the syscall used. For example, on Linux, positional use preadv or prwritev, and streaming uses readv or writev. With positional, you provide an offset and it will seek to that position and perform the operation. While with streaming, the operating system keeps track of an offset internally. So positional allows multiple threads to work on the same file without modifying the kernel file offset. Positional is usually better, but the file descriptor needs to point to something seekable. Pipes, sockets, character devices are not seekable. So std out, which is usually attached to a TTY, isn't seekable, so we can't use positional. One more thing, using write streaming all is equivalent to creating a streaming writer, writing bytes, and then flushing, which is almost equivalent to creating a writer using the writer function instead of writer streaming. The difference is that writer defaults to positional reading, so it will perform a positional syscall, but fall back to streaming if positional fails. So using writer streaming right away will skip a failed syscall. Okay, let's now focus on what we really care about, async await. And friends. This is like the third time async await is introduced to the language, and at the beginning there was a big focus on function coloring. This idea is that once you start using async, it poisons every function that uses async or await. For example, in languages like JavaScript or Rust, once you define a function async, every function that awaits it needs to be async. People are probably going to keep talking about it. Some people say that now Zig is colorblind or colorless, but others argue that the color problem is still there because now we need to pass around an IO argument to every function. But I think they are focusing on the wrong problem. The issue with what many languages do is split the word in two, the synchronous part and the asynchronous part, which are incompatible. So when you develop an application or library, you need to pick between asynchronous or synchronous or duplicate code to have both. What the new IO interface enables is that you don't need to choose. Zig has found a way to make writing code work regardless of the concurrency model you want to use. So the attention is much more focused toward reusability and expressiveness. What I mean by that is that one can define or express that a piece of code can be executed concurrently or in parallel or asynchronously, but doesn't have to. Now the execution model is decoupled from the code, from the logic. If you read articles or forum posts or if you watch videos, you are probably going to see or hear the term asynchrony, which was made popular by Loris Crow in his article "Asynchrony is not concurrency." In short, asynchrony is the possibility for tasks to run out of order and still be correct. Asynchrony means it can be concurrent or parallel or not. It can be synchronous too. So in Zig, when you have several tasks that can be run concurrently or in parallel or simply out of order, you can express that using io.async. It has three parameters: the IO implementation, the function you want to execute, and the list of its arguments. And it returns a future. A future has two methods, cancel and await. So once you have a future, you can call await to wait for the result. Let's see it in action. For the incoming examples, I've defined two functions. One to log messages with the current timestamp in milliseconds, and another one to represent some long-running tasks. I've called it work. This function is just going to sleep for the number of seconds specified as an argument. It will print the name of the task and return the number we gave it. By the way, this could be any function. Here I'm using an IO parameter just to be able to sleep, but this would work with functions that don't need an IO parameter. I'm also using some code to measure the total time, but I'm going to omit it from the slides so we can focus on what really matters. To execute the function asynchronously, all we need to do is use the async function, give it the work function, and the list of its arguments. And we get a future. When we call async, the work function is either called immediately or ready to be called. To wait for the completion of work and get its result, its return value, we need to call await on the future, and that's it. Running this program isn't really interesting. It's just going to call work, sleep for a second, and return. Let's add 6 or 7 new async awaits. I now have 8 tasks that will all sleep during 1 second. If I run it, the 8 tasks are going to run concurrently and the total execution time will be about 1 second. Now, what's important to remember is that saying that async await is going to run your code asynchronously is incorrect. Take note, because this is going to be on the test. The only thing async await do in Zig is to decouple the calling of the function from the returning of the function. That's it. And that's important to remember because if I change IO to be single-threaded blocking, then the function calls are going to be executed sequentially, one after the other, and the total duration is going to be 8 seconds. That's the real power of this new I/O interface. You can now write code, express asynchrony using async await, and let the user pick the concurrency model she wants. Now, if your app requires concurrency to work properly, you can force it by using io.concurrent instead. But be careful, your I/O needs to support concurrency or you will get an error. Talking about errors, let's see what happens if our work function returns an error. I modify the work function to return an error when the name of the task is error. So now calling future.await returns an error union type. So if you want to access the actual result, to, for example, calculate the sum of all the results, then you need to use something like try. If all tasks succeed, then it works fine. But if one of the tasks fails, then using try will bubble up the error. So this is fine, but it is suboptimal, because if the first task fails, then awaiting for all the following tasks is just a waste of time. What you want to do is use try and await together. Unfortunately, this is not enough, because if one of the first await calls returns an error, then try will exit the current function and the following awaits are not going to be executed. Futures are resources that need to be released, so failing to await one is a programming error. That's when cancellation comes in. After each async call, you can use defer to cancel a future with the cancel method, or you can use a defer block. What's important to understand is that await and cancel have pretty much the same behavior. The only difference is that cancel will request the cancellation of the future. From what I understood, I/O implementation will, at relevant times and places, check if a cancellation was requested, and if it was, will exit early by returning an error.cancelled. In any case, cancel will return the same type of result than await, and that makes it easy to free resources. To illustrate that, I'm going to shamelessly take the example 7 from Andrew Kelly's article. Here we have the doWork function that allocates a new string that the caller is responsible for. So using defer, we can check if cancel returns a value, and if it does, it means that the future was completed, and we can free the allocated memory. Otherwise, cancel returns an error which corresponds to the error of the failed task, which in this example can only be out of memory, so we don't do anything. Because cancel and await are idempotent, this defer statement handles both successful and failed calls. But if you only want that behavior when it fails, you can use error defer. Okay, one more thing about cancel that I wasn't very clear about. When cancel is called, the doWork function may not be completed. It may not even be started. If that's the case, the function will start running until it either returns an error or returns normally. To make sure everybody understood properly, let's see what happens if every try await call succeeds. Then at the end, when we exit the scope, the defer instructions are going to be run in reverse order. So b.cancel is run first. Because b was successful, it returns a slice that we can free. And the same thing happens to the future a. Now, a different scenario. Let's say that try a.await returns an error. Then it skips the end and executes the defer instruction starting with b.cancel. If b is already completed, then we get a slice and we can free it. Otherwise, if, for example, it hasn't started, it will start running. If the first instruction fails, then it will return an error that will be processed by the else branch of our defer. But if it doesn't fail, the execution continues, it will print a message, and then it will call io.sleep, which should return the cancelled error that is caught by this catch. And then it will return the slice that will be freed. Finally, the second defer will be executed and a.cancel will return whatever error doWork returned. And that's it. I hope that was clear enough. Okay, I wanted to talk about group and select in this video too, but I'm going to stop here because it's already quite a lot and I didn't want to rush it and do a bad job. So see you in part 2. By the way, I lied. There is no test. Ha! Got him. Got him good. Lol. I can't read.